consider a beam that supports weight in motion. That is a perfect example of a complex weight distribution. If you look carefully here, you can see the numbers. That is a rail car that carries containers. The 40 and over 20 means the end of a 40-foot long container, or 20-foot long container. That is the end. From here, from this point, all the way to this point right here, we can put either a 140 or 220 containers. And here in the center, it tells you the weight limit. If you have one container, any size, the weight of that container should not be over 117,800 pounds. That is the maximum weight of a single container. If you have two containers, it gives you in the bottom, the limit is 56, half of it, half of that number, 57,500 pounds. If you have a longer container, like here, you have 40, you have two 20s, 140 feet, 145, 148, 153. That is the maximum length of a container you can put on a rail car. If you look on this side, the 53 is too far from the end of the container. If you look from the other side, here the 53 is at the end. Why? Because the coupling here is shared between two containers, and that is a fixed coupling. This end, the coupling is not fixed, which means this end will have two axles. This end will have one axle and shared with the other axle of the other rail car. The challenge here, the mechanical challenge, the calculation, is split into three issues. First, the weight. The weight have to be distributed between the two ends of the beam. That is easy to do if you have a very thick vertical thickness is so high, so it makes the weights to be distributed on both ends without having a lot of bending and curvature. It's not going to touch the rail. That is the weight, which means the mass of the weight of the contents multiplied by the gravity of the earth. The second problem is the torque. The torque is the distance between the center of mass of the container and the point of support. Here you have 2 points of support because you have two ends. One end have two axles here, and the other end have two axles. So if you have one container in the middle, you can see the support in the middle is a point, not a line. Here is a point of support, and if you go inside and you look, you are going to see a point where you can drop the container on it, and it's going to hook it vertically on that point right here, and another point right here, and a third point right here. So the support is in points. The central point, this point, the weight is transmitted to the end, so the support, the contact with the rail, by the beam, the entire beam, which is a massive structure weighing 30 tons. The rail car itself weighing 30 tons. 30 tons, somewhere between 70,000 pounds. So that is the second challenge. After the weight, that you have to distribute the weight equal between the two axles, the two ends, the two support points. Why do you do that? Because if you have too much weight on one side and less weight on the other side, you are going to have imbalance on the rail the rail is going to be pushed down in one point and pushed up in the other point. You are going to move the rail or stress the rail on the dirt or the gravel. And that stress can push the car. The car can jump off the rail if you have vertical imbalance in weight. The torque issue, which is the distance between the center of mass multiplied by the weight, the distance between the center and the axle of support, or the point of support, multiplied by the weight, that will give you the torque. The torque works when you make a curve. When the rail runs into a curve, the rail is curved. Here is where the torque can push the wheels from side to side. And if the weight is light and the speed is high, the rail car can jump off the rail. So you do have to have weight to push it down. You have to have the torque calculated such that the lateral force does not exceed the ability of the wheels to stay in the groove between the two rails. Each one of these wheels is slanted from side to side, so it is longer inside, it is shorter outside, or the diameter inside is long. Inside means between the rails is long. And the diameter outside is smaller, so the wheel can stay between the rails without having to jump in a curve. And that is affected by the torque. So we now discuss the weight and the torque. Then you have the third equation that is used in civil engineering besides the weight and the torque is the inertia. Inertia means the torque multiplied by the arm or the distance between the center of mass to the point of support multiplied by the angular velocity squared. We can call it the angular acceleration. That is the inertia. The inertia works when you are under speed or acceleration. Whenever you speed, you are not speeding a point. You are speeding a multi-body mass that has a center and the mass distributed around it. That third equation, which is the inertia or angular inertia, will affect the motion, the state of motion in many situations, especially in the linear situation. When you have a linear acceleration, if that inertia can control how fast or how quick can that car be pushed up. If you look here carefully, this on the contact between the wheels, right here, between the wheels and the frame, the chassis, you discover that it's an inverted U shape where the body is sitting on the axle of the wheels, free from the bottom, and a U shaped from the side and the top. So when the wheel is pushed up, because if you have a bump, the train is running 90 miles per hour and the weight is not balanced, or the structure of the soil hard in one area, soft in another area, you will have a vertical jump. If the vertical jump exceeds the thickness of that vertical U-shaped supports around the axle, the rail car will jump off the axle. And you are going to have a separation. The wheels will go one way and the car will be thrown to the side. Those are the three equations that you have to take into consideration when you solve a mechanical problem that has multi-body mass, which means a large mass with too many support centers and too many contact centers, and the weight distribution is challenging. Vertical, sideways, and longitudinal. So your three equation will be the weight distribution equation, which means the mass times the gravity, at each spot, each point of contact, each point of support. And the second equation will be the torque around each point of support, which is the mass times the distance between the center of mass and the point of support. And the third equation will be the angular acceleration, that is due to the distribution of the mass around a point. Here you have too many points. You have to consider two ends, which mean two support points, and each end have two axes. So you first try to simplify the problem with having two ends only, and you leave the minute details for the computer design.